Hi, welcome to this video series on polar plots, a first step towards Nyquist plot. So in this video we'll see how to plot a polar plot for a simple open loop transfer functions. So let us consider the first polar plot with open loop transfer function given by 10 by s plus 2. So we have a pole located on the left hand side of the s-plane at -2. So for this polar plot, we are supposed to have both magnitude as well as the phase for different values of frequency. So this is what we are trying to do now. So for values of s is equal to j omega, so we'll substitute s by j omega. We'll have this as the magnitude expression and this is the phase expression. So now we will vary the value of omega from 0 to infinity and try to find out how does the magnitude and the phase of this particular transfer function change. This is how the values of omega changing from 0 to infinity. So substituting the value of omega starting from 0 to infinity in terms of 1, 10, 100. So we're going to get the magnitude as 5, 4.4. Okay, these are the magnitudes and this is the phase. So in order to plot the polar plot, so since this polar plot has got both magnitude as well as the phase in its representation, so you can see here this is the 0 degree line, horizontal line, and we have this as minus 90 degree line, this is minus 180 degree, and this is minus 270 if you go in the clockwise direction. If I go in the anti-clockwise direction, then this is plus 90, this is plus 180, this is plus 270 degrees. Since we are going with an angle of minus 26 degree, so since it is going in the clockwise direction, this is in negative angle. Now the magnitude of this angle is 26 degree. So it is minus because you are going the clockwise direction. So this first line corresponds to a line of minus 26 degree. Second one corresponds to minus 78 degrees somewhere here. You can see from here you come down an angle of minus 78 degrees, which corresponds to negative. Similarly, we have minus 88 degree, which is very close to minus 90 degree line here. So these are the lines indicating the angle corresponding to minus 26, minus 78 and minus 88. Now these are the lines on which I am supposed to trace this magnitude of 4.4, 0.98, 0.09, all those things. So here you can see this is the magnitude 5 at an angle 0 degree. This is magnitude 4.4 at an angle of minus 26 degrees. This is magnitude almost 1 at an angle of minus 78 degree. And this is magnitude 0.09 at an angle minus 8 degree. So we are supposed to join all these lines, that is this, and finally it goes here. So ultimately it will look like this. So this is the polar plot for this particular transfer function with the value of omega as 0, the phase angle is 0 degree and the magnitude is 5. As the value of omega increases, phase angle is keep going in negative direction and it goes to minus 90. So when the phase goes to minus 90, the magnitude goes to 0. So that's what is this table says. You can see it is going from 5 to 0, magnitude is keep reducing, whereas the phase is going from 0 to minus 90 degree. It's always negative. It's monotonously making from 0 to minus 90 degree. So this is how we can plot a polar plot for a very simple transfer function. Let us see the next polar plot. Now here you can see we have two real time poles on the real axis. One is at minus 4, other is at minus 10. It has got a constant gain of 20. Let us see how does the plot of this look like. This is a magnitude expression. If you can see in the denominator we have under root of omega square plus 4 square. Similarly we have for the second term. We have the phase equation, which is minus times of imaginary by the real value, and again minus times of omega by 10. So this is the magnitude and phase equation. So as per this magnitude and phase equation, if you vary the value of omega from 0 to infinity in different values, you can see this is how the magnitude changes from 0.5 to 0. So this is extreme value. The angle changes from 0 to minus 180. If you can see here, this is, we are not shown it in detail, but ultimately the magnitude is 0.5 at 0 degree, and you can see it is going negative. You can see it is going negative and it surpasses minus 90 degree also. Finally it enters minus 180 degree. At that point the magnitude is 0. So this is the polar plot for this particular transfer function having two poles on the real axis of the S-plane. Let us see the third one, so in which we have three poles on the left hand side of this plane at -1, -2 and -5. Let us see the magnitude as well as the phase equation. This is the magnitude and phase equations, which is very evident. You can able to easily understand this magnitude and phase equations. Let us again change the value of omega from 0 to infinity and see how does the magnitude and phase changes. This is how the magnitude is changing from 1 to 0 as the value of omega changes from 0 to infinity, and this is a phase angle changing from 0 degree to -270 degree. You can see it's always keep going negative, and it is reaching -270 degree. At that point the magnitude is 0 degree. So this is the plot of that particular transfer function. You can see magnitude is 1, the phase angle is keep reducing, meaning it is keep increasing in the negative direction. It passes -90 degree, and it also passes -180 degree, and finally reaches -270 degree. By that point the magnitude is 0. You can certainly notice that, so as the value of omega changes from 0 to infinity, it is going from 0, -90 through -180, finally to -270. We can actually find out at what frequency the phase angle is -180 degree. So for this particular example, when value of omega is 4.12, the phase is equal to -180 degree. So this is one of the important parameters which we'll be looking for while doing the Nyquist stability criteria. So we'll move on to the next plot. Now you can see we have two poles, but one of the pole is on the at the origin. The pole is at the origin, other is on the left hand side of this plane. This is how the magnitude equation looks like. This is a phase equation. Since there is a pole at the origin, so we're going to have -90 degree contributed with that, and this is -sin of omega by 8. So again, by changing the value of omega from 0 to infinity, you can see this is how it is changing. So this is value of omega, the corresponding magnitude, the corresponding phase. So to obtain this, you simply substitute the value of omega as 0 or whatever the value, so you'll get both magnitude as well as the phase. So upon looking at this, you can see that phase is varying from -90 degree, and you can certainly notice that the magnitude is infinity. So let us represent this as infinity. Since it is -90 to -180, it will be there in the third quadrant. So this is first, second, third. So the plot always changes in the third quadrant. Whereas in the previous case, you can see since the phase was varying from 0 to -270, it was there in fourth quadrant, third quadrant, as well as it entered the second quadrant. So depending on what is the phase angle, it takes the quadrants of your plane. So since the magnitude is infinity, let's go back. So since the magnitude is infinity, let us consider this as infinite, and it is phase is keep increasing, and finally it goes to -180 degree phase. At that phase, the magnitude is 0. So this is how we can plot the polar plot of a transfer function having a pole at the origin. This is again a different transfer function where you have a pole at the origin, and of course you have two poles at the on the real axis. So again, this is a magnitude and phase equations. If you can see, this is how the plot is changing. It is going from infinity magnitude. The phase is -90 degree. That's what is this first thing, and it crosses -180 degree. So it crosses -180 degree at 7.07 radian per second. So, and then finally, as the value of omega goes to infinity, magnitude becomes 0. The phase angle is -270 degree. So that's why it is entering this -0 at -270 degrees. This is for the fifth plot, having one pole at the origin and two poles on the left hand side of this plane. Let us see a special case where you have poles on either side of the S-plane, that is both on the left hand as well as the right hand side. This is how the magnitude equation looks like. There is no change here, but you can see the phase equation is -tan of omega by 2 for this. This is -tan of omega by -5. So this -5 we can eliminate by taking it as 180 minus of tan of omega 5. So finally the phase equation reduces to this form, which is minus tan inverse of omega by 2 minus 180 plus tan inverse of omega by 5. So now for this also we will change the value of omega from 0 to infinity, try to find out what is the magnitude and the phase of the plot. You can see this is the phase part of it. So we're not too much worried about the magnitude because they'll be very less. So let us trace how does the phase changes here. When it is 0 degree, when the omega is 0, it is minus 180 degree. Even when omega is equal to infinity, you can see this will become minus 90, this will become plus 90. Both of them will cancel out. You will again end up with minus 180. You can see when omega is equal to 0, it is minus 180. When omega is equal to infinite radian per second, then also the phase is minus 180 degree. So in between 0 and infinite omega, the phase changes actually in the second quadrant. You can see this is the first and the second quadrant, because in second quadrant the angles what we have is minus 270 and minus 180. Since it is between minus 180 to minus 180, it actually goes in this quadrant only. You can see there is a phase angle which is going beyond minus 180, that's why it goes to second quadrant. You can see finally it is entering at an angle of minus 180. So this is how it is entering. Suppose if this was minus 270, it would have entered this way. Now since it is minus 180, it is entering this. So you can notice this change of entry angle for this origin, that is magnitude 0, it's happening at minus 180 degree. Just go back and see in the previous problem. Now here you can see it is entering 0 at an angle of minus 270 degree, which was this. You can see 0, it is minus 270 degree. So this is an indication of how does the phase angle is minus 270 degree and the magnitude is 0. Whereas in the problem that what we are referring, or the transfer function what we are referring, the phase angle is minus 180 degree, magnitude is 0. So that's why you can see it is entering in this particular line of minus 180 degree. So this is actually minus 180 with a magnitude of 1. So let us move on to plot number 7, where you can see, you can just notice the difference between the previous and this one. Here you can see it is 10 divided by s plus 2 into s minus 5. Here it is just only that plus minus has been interchanged. So interestingly, you can see there is a major difference between locating the pole, what is the magnitude of the pole which is there on the right hand side. Since this is s minus 2, we have, this is the phase equation. So there's a small change in the phase equation compared to the previous one. In the previous one, this was negative, this was positive. Now it is interchanged because of the position on the right and left hand side of the S plane. Let us see what is the change in the plot. You can see the plot is actually as the value of omega changes from 0 to infinity. Again, the magnitude is, there is no change in the magnitude expression from the previous problem. The magnitude is again varying from 1 to 0 as the value of omega changes from 0 to infinity. But you can clearly notice the phase angle is changing for this particular transfer function from minus 180 to minus 180, but the phase is always lesser than minus 180. You can see it is minus 178, minus 164, again minus 179.1. So it goes in the third quadrant. So this is one of the important thing that is to be noticed. So while finding the phase angle, or while finding the phase angle and plotting the graph, we need to be careful here. So this minus 178 actually comes in the third quadrant, whereas the previous problem, so this minus 181 comes in the second quadrant. So otherwise, suppose if you are a bit careful, because it is starting from minus 180, ending at minus 180. Since the angle is minus 181, minus 195, it goes in the second quadrant, whereas in the next case, that is in this case, it is minus 178, it goes in the third quadrant. So we need to be careful while identifying these angles. So let us see the next problem. You can see this is similar to that. You can actually find out it is minus 270 plus tan inverse of so and so. This is how the phase angle is changing, and the magnitude. Magnitude is varying from infinity to 0, whereas the phase angle is going from minus 270 to 270, and in between that it is going minus 276, minus 236, and then this lies in the second quadrant of this. So this is the transfer function, and this is the polar plot of this. Maybe in the next plot we will see this is moving on the right hand side depending on the position of these poles.